Okay, go ahead.
Thanks.
It's all yours. Yep.
Thanks, Yuan. And yeah, great to see everyone back. The numbers are dwindling, so thanks for hanging on in there. Just as previous times, I've put the link to the slides in chat if you want to kind of follow along. Now, so let me just quickly recall the main things that we did last time. The whole point of last lecture was we showed that the exponential function is Diophantine. Okay, and our next goal is to show that the class of Diophantine relations is closed under bounded quantification. This last time we showed is actually enough to get us the main theorem that we want, because once we have the power of bounded quantification, we can do, for example, minimization as well as primitive recursion. So in order to do this, in order to get bounded quantification, we have to prove that a few other functions are Diophantine. And here are some of them that we will need. So we have the binomial coefficient, we have the factorial, and we also have this weird product thing. And I'm going to briefly talk about how one would prove the above. This will be very scant on the details. So let's see. Let's start with the binomial coefficient. So the basic idea is, okay, we already know how to define the exponential function. So we're going to use that to define the binomial coefficient. And the main point is that if you take the exponential, like u plus 1, where u is some integer, if you take u plus 1 to the n, okay, and you look at the base u expansion of that, then actually the binomial coefficients are going to appear as digits whenever u is large enough relative to n. And the formal statement is as follows. So if you have k less than or equals to n, well, so that's the only case where where we care about the binomial coefficients, right? And if u is greater than 2 to the n, okay, then the binomial coefficient n choose k is actually the remainder of this number. So this can be defined using the exponential function when divided by u. Okay, and so the main point here is that this definition here is Diophantine once we know that the exponential function is Diophantine, which we showed last time. Let's briefly look at the proof of this lemma. The whole point is first, well, if in order for n choose k to be a remainder when divided by u, first of all, it has to be less than u, and that is true by assumption. But the main point here is, well, why is it actually congruent modulo, that floor function thing? Well, the point is use the binomial theorem. Okay, so take u plus 1 to the n, use the binomial theorem to expand it, and then we divide every term by u to the k, and we can break up the sum into 3 pieces here. The first sum is the terms where you actually have negative powers of u, okay, because of the division by u to the k. So this first sum, you can show with some inequalities that it's going to be less than 1. Okay, so that means that it's going to be erased, right, when we do the floor function. Because the rest are going to be integers. So this second term here, well, that's just n choose k, right? That's what we are interested in. And the third term, well, not only is it an integer, but actually it is divisible by u because it has each of them have some positive power of u in them. So we have something that's divisible by u plus some integer plus something that's less than 1, where you take the floor function, the first one goes away, and so n choose k is the remainder. Okay, so this proof was short enough that I decided that I just give it anyway. But the whole point here is that we don't actually care about this statement being true. The whole point is that now we have a Diophantine definition of the binomial coefficient. All right, that's one thing down. Now the next one we want to do is the factorial. So usually we define, one often defines the binomial coefficient in terms of the factorial, but actually you can do the reverse. So if we have the binomial coefficient, we can actually define the factorial. Okay, so and this is the fact that gives a definition. So I'm not going to prove this. This is the inequalities involved are fairly tedious, but again, the point is the right-hand side here is a Diophantine definition. Once we know that the exponential and the binomial coefficients are Diophantine, which we do. So this gets us the factorial function being Diophantine. And then using that, we can now go back to that weird product thing. So this is the kind of the main lemma that allows us to define the product. I want to kind of wave my hands about it. So, okay, let's say we have A, T, and Y. Okay, those are the inputs for the product. And we are interested in defining this product here. So it's the product of A plus KT for K less than or equals to Y. So this is basically like a product of a finite arithmetic progression where the first term is A and each term you add T. And then you go for Y many terms, right? So that's the meaning of this product here. Now, how can we define this? Okay, so suppose that we have some Q and some U, which satisfy some technical conditions. Then you can define this product by taking a certain number and dividing it by U and taking the remainder. Now, this thing here, right, this number here, I've written it as a product, which is of the form that we want to define. So you might think that, okay, this is suspicious because, well, how do we know this is Diophantine, right? We're trying to show that this is Diophantine in the first place. However, this product is slightly different. Notice that over here we have QT instead of having an A. And this enables us to kind of rearrange this into the following form on the right. So here, again, it doesn't matter so much what this is. The point is that this is Diophantine because you have exponential and then factorial and then you have binomial coefficient, right? So this guy is Diophantine. And so this lemma, provided we can find such Q and U, is going to give a Diophantine definition. And so apart from the proof of this lemma, you still have to do some work in showing that, you know, for any A, T, and Y, we can find Q and U that serve this purpose, but I'll skip those details. So the main point is that, okay, just building upon previous things, we can again give a Diophantine definition of this product. Okay, well, now let's go to bounded quantification. So this is the theorem that we want to prove, right? This is the theorem that says that the Diophantine relations are closed under bounded quantification. So we're saying that, okay, if you have P, which is Diophantine, then the set of B comma X such that for all K less than or equals to B, there is some Y such that P, KB, XY is 0. This is also a Diophantine set. Okay, so how do we prove this? So the functions that we just showed are Diophantine are going to be useful. And I'm again going to skip many of the details, but I want to talk about some of the kind of tricks that help us do this. The first thing here, so let P be a prime, okay? And okay, the first fact here doesn't really rely on P being a prime, but if you have a P that divides P of Y, and P has absolute value greater than P of Y, then P of Y must be equals to 0. Okay, so this is a completely trivial fact, but it is useful because, well, now we've kind of, instead of specifying that something is equals to 0, we can kind of split it up into two pieces here. And if both pieces are satisfied, then we know that this thing is equals to 0. And why is it helpful to split it into these two pieces? That's because of observation 2. So observation 2 basically says that, well, if you're considering mod P, okay, then and you have some polynomials, then things play well. So if you have Y prime, which is the same mod P as Y, which is equivalent to Y mod P, then P of Y prime is also equivalent to P of Y mod P, right? That's just this is just a basic property of polynomials and modular arithmetic. And so observation 1 combined with observation 2 kind of allows us to shift from, instead of considering y, we can consider some other y prime, as long as it's congruent to y mod p. Finally, another observation. This has come up before when we were talking about the sequence numbers. So if we have some c and some q, such that p divides 1 plus c times q factorial. So think of this as saying that p divides 1 plus some multiple of q factorial. Well, then p must be greater than q. Okay, because, well, if p is less than q, right, then it's going to divide q factorial, and that means that it cannot divide this the sum of c times q factorial plus 1. So that's another useful observation that that is used in the proof. Now on the next slide, I'm going to show you the proof, but it's a bit gnarly, and I'm not really going to talk about the details. So here's the sketch of the proof. The big steps are as follows. So we're given some p, right, and we're trying to define this. We're trying to give a Diophantine definition of the like the bounded quantification of p. So first, we're going to define this auxiliary polynomial q. Okay, and the main point of q is that the exact value of q doesn't really matter. What matters is that q is big. Okay, so like, for example, this first point, q of bux has to be greater than b and greater than u. And second is that q of bux has to be greater than like all these values of p. Okay, so think of q as just specifying some large bound, and within which, you know, we can sort of, that's the domain that we want to focus on, you know, the domain that's bounded by q in some sense. So once we have this q here, this q can always be defined. This is something that you might be asked to do in an analysis class. Once we have that, right, then we can give this definition as follows. So for all k less than or equals to b, there is some y such that p of kb xy is 0, if and only if there are these variables such that these conditions hold. And yeah, as I said, I'm not going to talk about it, but in order to show that in order to prove this equivalence, the observations on the previous slide are going to be useful. Okay, so if you accept this theorem that the Diophantine relations are closed under bounded quantification, then this completes the proof that a function is Diophantine if and only if it's recursive. So remember, like this theorem was the main theorem that we were working towards from maybe like 30 slides ago. One direction is easy, like if a function is Diophantine, it's clearly recursive, but the converse is highly non-trivial, and we have just completed the proof of the converse. I mean, well, I mean, I've waved my hands a bit, but you know, I've given you the ingredients to complete the proof in some sense. So yeah, I think this kind of concludes the number theoretic portion of this lecture. Before we continue with this, are there any questions? Okay, cool. So from now on, we're going to just, you know, we will now leverage this theorem, the theorem that a function is Diophantine if and only if it's recursive, and we'll use it to circle back to Hilbert's 10 problem and other things, talk about applications of this theorem. So the first application here is, so we know exactly what the Diophantine functions are. That allows us to also pin down what the Diophantine sets are. So remember, a function is Diophantine if its graph is a a Diophantine relation. Right? It's defined by some Diophantine equation, but a Diophantine set is just it's a set of natural numbers, right, which is defined by some Diophantine relation. And so these sets are exactly the recursively enumerable sets. So these are Patrick defined them in his lectures. One way to define it is these are the range of recursive functions. Okay, so for every recursively enumerable set, there is some recursive function whose range is equals to that set. Let's talk about the proof of this theorem. It is quite easy once we have the big theorem that we just finished. So in one direction, suppose that S is a Diophantine set. Okay, so because it's a Diophantine set, so I can fix a Diophantine definition as follows. Right, so S is the set of all x, such that there exists y, Pxy equals to 0, and P here is a Diophantine equation, right? A polynomial with integer coefficients. Now, okay, there are multiple ways we could proceed from here. One way is to show that S is recursively enumerable. We could construct a program which actually just lists the elements of S. And the basic idea is that, well, you just go through all of the possible y's and all of the possible x's. And whenever you find some x and y, which makes Pxy equals to 0, then you know that x is in S, right? So you output that x, like you put that x into the list. And so if you do this forever, eventually you'll list every element of S, and that shows that S is recursively enumerable. So that's kind of one way to do it. Another way is to view the recursively enumerable sets as projections of recursive sets. So this is an equivalent way to define the recursively enumerable sets. They are the projections of recursive sets. So in this case here, I've chosen that approach. We have the recursive set of x comma y, Pxy equals to 0. This is clearly recursive, and S is the projection of it. So S is recursively enumerable. Okay, so that's one direction of the theorem. Now let's do the other direction. So now we are assuming that we have a recursively enumerable set. We want to show that it's Diophantine. So this is the one where we have to use the non-trivial theorem we just proved. So suppose S is recursively enumerable. Well, then S is the range of a recursive function. So let's call that function f. Let f be a recursive function whose range is S. Now we showed that recursive functions are Diophantine, so we can write down a Diophantine definition for what it means for z to be equals to f of x. Right, there must be some Diophantine equation that defines it. Then notice that, well, x is in S if and only if there exists z and y such that Pzxy equals to 0. And so, oh, wait, did I? Okay, so sorry, I messed up a little here because I should have swapped the x and the z's. Sorry, so I should have said that then z is in S if and only if there exists x such that there exists x and there exists y such that Pzxy equals to 0. So sorry, I got mixed up with the domain and range here. So small typo here. And yeah, but that is a Diophantine definition, right, of S. So that completes the proof of the theorem. Any questions here? All right, so now let's go back to Hilbert's 10 problem, finally. Section 2, finally, applications to Hilbert's 10 problem. All right. So the main theorem here about Hilbert's 10 problem is that it is unsolvable. And in fact, it is unsolvable in the following way. There is a single Diophantine equation, P, such that there is no recursive function that solves it. Right? So specifically, what I mean is this: there is no recursive function f. So f is a function from the natural numbers to 0, 1, such that, well, f of x tells us whether the equation p of xy equals to 0, where x is fixed, has a solution or not. So what I mean is that I'm thinking of this p not as a single equation, but as parametrizing a family of equations. So the y's here are the variables, and the x here is the parameter. As we vary each x, right, for x equals to 0, x equals to 1, x equals to 2, we get a different Diophantine equation, okay? So that gives us a family of Diophantine equations. And figuring out which of these have solutions, that is already algorithmically unsolvable. There is no recursive function that can tell us whether it has a solution or not. Okay, so I mean, what does this have to do with Hilbert's 10 problem, right? Remember that Hilbert's 10 problem is asking for a general procedure to solve every Diophantine equation. In this case here, we're not looking at every Diophantine equation, we're just looking at a specific family of Diophantine equations. And that's already unsolvable. So of course, Hilbert's 10 problem in general, as a corollary, is also unsolvable. Okay, let's prove this theorem here. The proof is very short. So what do we do? Well, first, let's fix a recursively enumerable set S, which is not recursive. Okay, so just a quick recap of what Patrick said previously. The recursive sets form a proper subclass of the recursively enumerable sets, right? Every recursive set is recursively enumerable, but not vice versa. And an example of a recursively enumerable set which is not recursive is the halting problem. So let's fix such a set. I mean, it doesn't have to be the halting problem, but if you like, you can just imagine that it is the halting problem. Now, we just showed that every recursively enumerable set is Diophantine, right? So as the S that we just fixed, it is Diophantine by the previous theorem. So we can fix a Diophantine definition for it. So over here, this is a Diophantine definition. And now, well, what is this F here? Well, F, right, the F in the theorem, okay, that's going to be essentially it's the characteristic function of this S, right? Because it's saying that, okay, if there is some solution to pxy, then F should output 1 when given x, right? Otherwise, and if there's no solution, then it should output 0. Well, that's the characteristic function of S. So since S is not recursive, its characteristic function is not recursive. So there cannot be a recursive function that solves, that determines whether each of these equations are solvable or not. Now, so technically this achieves our goal, the goal that we set out at the very beginning, which is to show that Hilbert's 10 problem is unsolvable. But there's actually quite a bit more that we can say. First, so it is unsolvable, but well, how unsolvable is it? And right at this point, I mean, this might sound like a vague question, but recursion theory allows us to quantify this. Recursion theory allows us to make this question precise. Okay, so what do I mean by that? Well, first, in order to apply the tools of recursion theory, we have to first go into the setting of recursion theory, which is the basic setting is the set of natural numbers. So we want to think of Hilbert's 10th problem as a set of natural numbers. And we can do that by fixing and encoding. So what we're doing here, and again, I'm sweeping some details here under the rug. What we're doing is we want to encode each Diophantine equation as a natural number in an effective way. One way to do this is, well, you can think of each Diophantine equation as like a finite sequence of numbers. Maybe like encoding the coefficients of each term and the degree of each term and the variables that make up each term. Right? So essentially, it's a finite sequence of numbers, and we know how to encode finite sequences of numbers as a single number. So that's one way to do it. But the actual implementation of this, the details don't affect our results. So I'm not going to give the details. The point here is that once we encode each Diophantine equation as a number, then we can think of Hilbert's 10th problem as a set of numbers. Namely, it is the set of E, such that E is a code for a Diophantine equation which has a solution. Okay, so there are some Diophantine equations which have solutions, so their codes will be in this set HTP, whereas there are other Diophantine equations with no solutions, so their codes will not be in this set. Right. Now we can study this set in the setting of recursion theory. And what we'll prove is that this set here, HTP, is equivalent from the computational point of view to the halting problem. So the formal statement here is that, well, HTP is Turing equivalent to the halting problem K. And what I mean by this, so again, this is a recap from what Patrick said. Patrick mentioned about oracle computation, right? So there's this idea of a Turing machine, and then there's this idea of a Turing machine which has access to an oracle. So what I'm saying here is that if we have a Turing machine with access to the oracle K, then we could compute HTP. Conversely, if we, sorry, I mean, the quantifiers was a bit wrong there. I'm saying that there is a Turing machine which has access to the oracle K, and it computes HTP. Conversely, there is a Turing machine that has oracle access to HTP and computes K. So this means that HTP and K are sort of computationally equivalent. In fact, a bit more is true here. So it's not just that there's a Turing machine that does it. In fact, the Turing machine has a very simple form. Basically, it only asks the oracle one question. Okay, so Turing machines in general, they can ask their oracle multiple questions in an adaptive way. But in this case, the algorithms are very simple. They only ask one question, and that's enough information for them to output the answer. So the formal way to specify that is many-one reducibility. So that's again something that Patrick mentioned. If you forgot what this is, that's okay, because I will remind you when we prove this theorem on the next couple of slides. So I'll go now for the next couple of slides is to prove this theorem. There are two directions, right? First, we have to reduce HTP to K, and then we need to go the other way and reduce K to HTP. All right, so here's the first direction, which shows that K is at least as complicated as HTP. So the result is, okay, HTP is many-one reducible to K, i.e., there is a recursive function f. So this f you should think of as implementing the reduction. What f does is that if you give f an input e, okay, then f of e is going to output some number. And the number that is produced by f, so f of e, the number, is in K if and only if the Diophantine equation coded by E has a solution. So think of this f as giving an algorithm to compute HTP if we have Oracle access to K, right? So the idea is f is telling you what question to ask. Like you're given input E, you want to say, well, you want to ask the Oracle K, is f of E in K? Then the Oracle gives you an answer, right? So if the Oracle says that, yes, f of E is in K, then your answer for whether the Diophantine equation coded by E has a solution should be yes as well. Similarly, if the Oracle says f of E is not in K, right, then your answer, you know that the Diophantine equation coded by E has no solution. So you're going to answer no. All right, that's the statement of the proposition. Any questions about that before we look at the proof? Okay, well, so let's construct such a recursive function f. The point here is this actually, the way to think about this, at least the way I think about this, is that the point is that HTP is recursively enumerable. Okay, that's something that we haven't said yet, but it's actually quite easy to show. And every recursively enumerable set is many-one reducible to K. So K is kind of complete in this sense. You know, it is the most complicated recursively enumerable set. But instead of relying on these results, which you may not be familiar with, let me just give a direct proof here. So what we can do is to consider the following machine. Okay, so this machine is, think about this machine as a way to kind of, it tries to solve Hilbert's 10 problem, kind of by brute force. So given input E and N, the N here, it isn't really important. It's just an artifact of how we define K. So just think of the input as E. This M is going to decode E to obtain a Diophantine equation. Okay, so E is the code for some Diophantine equation. So M is just going to figure out what the equation is. And then M is going to try all of these tuples X one by one to see if it's a solution. And if M finds such an X, right? If M finds a solution, then it's going to halt. Otherwise, it's never going to halt. Right, so M, if there's no solution, right, then M is just going to keep searching forever and it's never going to halt. If there is a solution, well, M is eventually going to find it, right? Because M is trying all of the tuples one by one in a systematic way. So it's going to find a solution eventually. Okay, so this is a this is a Turing machine, right? And well, it's an informal description of a Turing machine. So it's implemented by some partial recursive function G. And now what this F is doing is F of E is F of E here is going to be an index for this partial recursive function, or you can think of it as an index for this machine above. So this probably only makes sense if you remember what the halting problem is, right? So remember, the halting problem is the set of all E, such that if you take the Eve machine and you run it on input E, then it eventually halts. So that's why we're talking about all these like halting things in here. Okay, so that's one direction, right? That shows that HTP reduces to K. Let's now talk about the other direction. So we want to show that K reduces to HTP. In fact, we'll just go ahead and show that every RE set is reducible to HTP, which in particular, because K is RE, so K reduces to HTP as well. Okay, so what does it mean here? Let's just go through the statement again, right? Because again, I'm just unpacking the definition of many one reduction. So what does it mean for S to be many one reducible to HTP? Well, now we want to find a recursive function F such that for each X, in order to determine whether X is in S, we can just check whether the Diophantine equation coded by f of x has a solution. So if this equation has a solution, then x is in S. If this equation has no solution, then x is not in S. Okay, so how would we define such a function? Well, this is where we're going to use the big theorems that we proved, right? So the fact that every recursively enumerable set is Diophantine. So let's start off here by saying, well, S is recursively enumerable, so therefore it is Diophantine. So we can fix the Diophantine definition of that. Well, then over here, we already see that we have some, essentially a Diophantine equation that tells us what we want, right? So X is in S if and only if this equation has a solution. So let's just output the code of this equation, and then we are in business. So this guy here is pretty much an immediate corollary of the fact that every RE set is Diophantine, which of course is a highly non-trivial fact, right? But once we have that, then this result falls out immediately. Okay, any questions about this slide or the previous? Okay, so what's the upshot of the two previous slides? Well, the point now is that we know that HTP is exactly as complicated as the halting problem K. And what I mean by what is my measure of complexity here? Well, you can either take relative computability as given by Oracle Turing machines, or you can take many-one reducibility. These two sets are equivalent in both of those senses. This now leads us to what I think is a very interesting question, which is no longer open, right? But it was stated and solved before Hilbert's 10th problem was shown to be unsolvable. So we're kind of going a bit backwards in history here. But going back to 1940, okay, so 1940 is around the time when the foundations of recursion theory were being laid. And one of the people responsible for that was Post. And in a very influential paper in 1944, Post had said the following. So I'm going to quote from his paper here, but with some reformatting and some paraphrasing. So Post was interested in talking about the degree of unsolvability of unsolvable problems. Okay, so an example of an unsolvable problem is Hilbert's 10 problem, right? Although Post did not know that. Now, what do we mean by degree of unsolvability here? If we have two problems, okay, and okay, let's say they're both unsolvable, but each of them is reducible to the other, then we can consider them to have the same degree of unsolvability. So this first point is, we've just seen an example of that, right? This HTP and K, they have the same degree because they are reducible to each other. Another thing might happen, so it's possible that maybe you have a problem which has lower degree of unsolvability than another. And what that means is that, well, maybe the first one is reducible to the second, but the second one is not reducible to the first. Okay, so an example of this would be, well, if you take any computable problem, okay, so any problem which can be solved by some algorithm or recursive function, well, then it's definitely going to have lower degree of unsolvability than HTP, right? Because one of them is solvable and one of them is unsolvable. So the unsolvable one is more complicated, has higher degree. So that would be the second scenario. There is a third scenario, which is sort of a priori possible within such a framework. You might have problems with incomparable degrees of unsolvability. And what that means is that, well, you have two problems, both of them unsolvable, and neither of them is reducible to the other. Okay, we haven't seen an example of this, but a priori, that's possible, right? So that was an important question early on in recursion theory. Let me now continue with sort of quoting what Post said. And so Post was interested in the following. Well, so among these unsolvable problems, these RE unsolvable problems, which include HTP and K and so on, well, there is certainly a highest degree of unsolvability. So this is given by the halting problem. This is what I mentioned just now, right? It's the halting problem is like the most complicated RE set. Every RE set reduces to it. So it is maximally complicated. And now Post is wondering about, well, this single question of whether among these problems, there is a lower degree of unsolvability than the halting problem. So of course, the halting problem below it, we know that the computable problems are definitely below it, right? The solvable ones. But the Post question was whether there are unsolvable problems which have a strictly lower degree of unsolvability than the halting problem. So he was wondering, right? So there are two possibilities, right? Either there is some lower degree, which you can think of as some intermediate degree, or maybe they're all of the same degree of unsolvability, right? So maybe we just have like solvable, and then above that there's like unsolvable, and it's either you are solvable or you are unsolvable and equivalent to the halting problem. That's a possibility as well, at least from the point of view of Post. So this question here, the question on the second half of the slide, became known as Post's problem, and it was solved maybe about 10 to 15 years later. So I'll leave Patrick to tell you the details about that. But for now, let me point out the connection between these incomparable degrees and Post problem. So in Post problem, in the second half, he's just asking for whether there is like a degree strictly in between, right? And I just want to point out that, well, if there are incomparable degrees of unsolvability, okay, then both of the incomparable degrees will be answers to post problem. So both of them have to be strictly between the halting problem and the solvable problems because they are incomparable, right? So, so in a sense, post problem is a rather modest problem. He could have asked an even more ambitious question, which is that are there incomparable degrees of unsolvability? And that was also eventually resolved. Any questions about this slide here?
Sounds good.
Cool. Yeah. So yeah, if you want to hear more about this, like if you want to hear the details, like a bit about the proof ideas and so on, like how this problem was resolved, make sure to go for Patrick's lectures. Yeah, that's what he hopes to talk about in the next series, in the next 2 hours after mine. For now, what I will do is, so I will depart from this topic and I'll talk more about Hilbert's 10 problem. What else is there to talk about, you might wonder? Well, actually, there is quite a lot, right? Hilbert's 10 problem was resolved in 1970, but there are still several variations and sub-problems that we can discuss. So that will be section 3 of this talk here. Now, I think now is perhaps a good time for a break. So let's take a 5-minute break here. And when we come back from break, I'll do the rest of the talk.
Okay, so there will be a 5-minute break and we'll be back at about 11:53 on the clock.
Right, well, depending on your time zone, yeah.
Depending on your time. That's right.
Yeah.
All right.
Okay, see you guys in a bit. All right, looks like we're back. So let's now talk about variations of Hilbert's 10 problem and also some sub-problems which are open. So since even though we know that Hilbert's 10 problem in general is unsolvable, but we can still ask, well, which sub-problems of Hilbert's 10 problem are solvable, right? Maybe there is no process that works for all Diophantine equations, but we can maybe have a process that works for all Diophantine equations, satisfying some special restrictions. Well, here are some examples, but this has been studied for a very long time, since antiquity. So one example is degree 1. So what do I mean degree 1? Well, what I mean is like, okay, you have some number of variables, all linear terms and integer coefficients, and you're asked, okay, are there integer solutions to this equation? Well, this is something that well, I guess you learn in high school or in college. Another example, which is known to be solvable, is one variable. So now we have a single variable, but you allow powers of the variable. So this is just polynomials in one variable with integer coefficients. And you're asking whether there is an integer solution. In other words, whether there's an integer root, right? That's the usual phrase that is used. So that's also well known. We know how to do that. Now let's move on to more complicated situations, things which you don't learn in school, probably. Degree 2 and 2 variables. Okay, this was solved by Lagrange, okay, using the theory of quadratic forms. So if you've taken a number theory course, then you're probably familiar with this. But yeah, this is already kind of non-trivial. But it is solvable, okay? And then for degree 2 still, but arbitrarily many variables. This was solved by Siegel, I think, in 1972. So again, over there, this one, yeah, you really need some advanced number theory to even make sense of the algorithm here. So that settles it for degree 2. and degree 3 remains open. Okay, so we don't know. We don't know whether there is some algorithm that solves Hilbert's 10 problem for equations of degree 3. In the two variable case though, quite a bit is known. And I won't try to survey all that is known here, but I want to give you an example of the things that people know. One of these things is the following theorem of Baker from the 1970s. So this is kind of it's what you would consider transcendental number theory, perhaps. Now, let's consider this specific kind of Diophantine equation. Okay, so it has two variables, x and y. The y just appears as y squared. And the x, well, it appears like on its own, but there's x cubed, x squared, x, and a constant. These a, b, c, d could be 0, but well, let's assume not all of them are 0. Otherwise, it's going to be pretty trivial. So we have this kind of equation here. This is a Diophantine equation with, it's of degree 3 and two variables. This is actually one of the forms of an elliptic curve. And Baker showed that the integer solutions to this equation, in other words, the integer points on this specific curve here, satisfy the following inequality. So their absolute value is less than this massive number. And by massive, I really mean massive, right? There's like 10 to the 6 here, and then there's a power 10 to the 6 here, and just throw on an exponential for good measure. So this is a really, really big number, but it is a finite number. And well, it just depends on these coefficients, A, B, C, D. What's the point here? Well, the point here is that there is a finite bound for all of the solutions to this equation. And well, how does that help us? Well, this tells us that there is an algorithm to decide whether such an equation has a solution, because you can just check all of the x and y's that satisfy this bound. There are only finitely many, so we can check all of them. And when we're done, eventually, well, then we can, if we have found some integer solution, then obviously the equation does have a solution. If we haven't found any within these bounds, then we know that there are none. So that's an algorithm. So this is an example of the kind of thing that people know. So this tells us that, okay, if you care about these specific kinds of equations, then it is solvable. But in general, for degree 3, it is still open. Okay, so that's degree 3. Well, how about degree 4 now? Actually, for degree 4, we know exactly what happens. And that's because of the following proposition. Given any Diophantine equation P, we can compute a Diophantine equation Q. Okay, so Q is defined from P in some way, and Q has degree 4. Furthermore, Q has an integer solution if and only if this P has an integer solution. So what is this proposition doing here? Well, essentially, it's reducing Hilbert's 10 problem to Hilbert's 10 problem for Diophantine equations of degree 4 or less. Let's look at the proof of this proposition. It's quite elementary. So the plan here is to define this Q. Okay, we will first construct a system of equations of degree 2. Okay, so we will have several equations of degree 2. And as we've seen before, if we have several equations of degree 2, we can combine them into a single equation by taking their sums, by taking the sum of squares. And of course, the sum of squares of things of degree 2, well, that's going to be of degree 4, right? It's not going to be of degree 2 anymore because of the square. Okay, so first, how do we get this system of equations of degree 2? Well, what we can do is, okay, if we have a term in P, in capital P, which has degree more than 2, well, we can replace it with a new term of smaller degree, which using a new variable. Okay, so maybe I think what I wrote here maybe doesn't correspond exactly, like the first sentence of this paragraph doesn't correspond exactly to the second sentence, but hopefully the idea is clear. So what we're doing here is, like, let's say we have some x to the 4, okay? Well, we can get rid of it by replacing it with xy, and then we just add a new equation that says y equals to x cubed. Okay, and so this degree 4 term has been replaced with a degree 2 term. So in that case, we're good. But now we have to worry about this y equals to x cubed, because now this is degree 3, right, greater than 2. So we could take x cubed and now replace it with xz. And then we can add a new equation, z equals to x squared. And now this is degree 2, and so we're happy. So the idea is to repeatedly do this process. Every time you see something of degree greater than 2, you make this kind of substitution, and eventually after finite time you're going to make everything degree 2, and then you take the sum of squares of everything that you have. That's how the proof goes. So the corollary, as I've already verbally mentioned, that tells us that Hilbert's 10 problem for equations of degree at most 4 is unsolvable, because we can reduce the original Hilbert's 10 problem to this sub-problem here. So basically what this tells us is that, there's no hope for number theorists to try to search for an algorithm to solve all equations of degree 4, right? It is unsolvable. It is equally unsolvable as the general case. Degree 3, however, that is still, it's still open, right? We don't know. Something important to point out here, this procedure that we did above in the proof, right, where we did this substitution and we came up with a new equation. So every time we do this substitution, we are adding a new variable, right? This, for example, x to the 4, we replaced it with xy, and y is a new variable that we're introducing. So this process is going to increase the number of variables by quite a lot, right, depending on the degree of the original equation. And this raises a natural question, which is that, okay, what if we, instead of looking at equations of restricted degree, well, how about equations of restricted number of variables? So people have also looked at that, but I'll be honest, I don't know that much about it. What I do know is that there is a result by Sun, sorry, by Sun, and he proved that if you have at most 11 variables, that's already enough to be unsolvable. But as far as I know, well, I think this is most likely not optimal. So yeah, there's still some gap here for the result to be improved in either direction. Okay, so we've just talked about restrictions of Hilbert's 10 problem based on degree and also based on number of variables. And yeah, over there, both of them, in both of these aspects, there are still various open questions. Another question that we might be interested in is, well, even for specifically for the solvable subproblems, we might be interested in their computational complexity. So if you have experience with CS, then you're very familiar with this notion. I'm not going to formally introduce this. I'll just kind of vaguely tell you what it's trying to do. So computational complexity is concerned with the time and or space resources needed to solve computational problems. In other words, they don't just care, okay, whether there is an algorithm to solve a problem. Well, they care about, okay, how much time is the algorithm going to need? How much space is it going to need? Things like that. And specifically, the computational complexity of number theoretic problems, such as factoring, for example. So you can think of factoring as a problem, right? This is important for cryptography, right? Things like the RSA cryptographic scheme, it relies on factoring being difficult. By difficult, I mean computationally intensive. So now one can ask, well, whenever we have some subproblem of Hilbert's 10 problem, which is solvable, well, we can ask, well, what is its computational complexity? That's a question that, again, there are many open questions here. I won't attempt to survey the field here, but I will say, let's come back, circle back to Baker's theorem that appeared a few slides ago. So this here is the theorem, just repeating it. So the algorithm that comes up from this theorem is terrible, right? Which you probably noticed when I mentioned it. Namely, we're doing kind of a brute force thing by checking all of the x and y below this absurdly large number. So this is a very inefficient algorithm. And so there's a natural question as to, can we get a better algorithm to solve such equations? Something that uses less time. So some people have done work into this, not this specific kind of equation, but some other kinds of equations. For that, I encourage you to read this paper by Le Goh from 2011. So I will give you the exact reference for this at the end of my slides. So I should mention here that actually this is a paper from 1979, but it was kind of expanded recently. That's why the date is 2011. But I find it quite readable, and I do encourage you kind of skim it at least if you're interested. Okay, so that's yet another kind of question that we might ask, right? Regarding these problems, like, well, even if it's solvable, we can ask, well, how efficiently can we solve it? And this kind of question, it doesn't just apply to Hilbert's 10 problem; it applies to any kind of computational problem. Here's yet another kind of question that we might ask. So yeah, the title, it's going to be a bit weird, right? We're saying, okay, we're taking sub-problems of Hilbert's 10 problem, but then we're going to generalize them, except that we're going to generalize them in a slightly different direction. Here's an example. So let's say we fix some k. Okay, so think of k being like a small number, like 2 or 3, okay? And the problem is, okay, if I give you a Diophantine equation, which has degree less than or equals to k, your job is to decide if it has solutions in the natural numbers. Now, this sounds very similar to Hilbert's 10 problem, but I would like to remind you that Hilbert's 10 problem, as originally stated, is asking for integer solutions, not solutions in natural numbers. Earlier in our lectures, like a week ago, we sort of immediately changed the scope from looking for integer solutions to looking for natural number solutions. And this kind of transformation, we have to be careful about how it affects the degree. Okay, because previously we were just looking at Hilbert's 10 problem in general. So we don't really care about the degrees of the equations that come out. But here we do care because now we're restricting the degree. So in one direction, everything still works. So if we can reduce Hilbert's 10 problem for equations of degree less than or equals to k, we can reduce it to the above problem. And this is done by, well, if we have an equation, we are interested in whether it has integer solutions. we can just double the number of variables and just essentially express each integer variable as the difference of two natural number variables. So, so that operation, that transformation, doesn't change the degree. So it gives a reduction. Conversely, that's not so clear. Okay, so it's not so clear whether we can reduce the above problem to Hilbert's 10 problem for equations of degree less than or equals to k. And the reason is because, well, so we do know of some kind of reduction, but the reduction doesn't preserve degree, so it doesn't actually work in this setting. And let me just remind you what the reduction does. So here's an example. Let's say we're interested in finding out whether this equation here, x1 squared plus 3x2 plus 2 equals to 0, we're interested in whether it has a solution in the natural numbers. Well, what we can do is we can consider the following equation instead, and we can ask whether it has a solution in the integers. And here we've taken each variable and replaced it with the sum of squares of 4 variables. And the reason why this works, I'm just recalling this from our discussion a week ago. The reason why this works is because of the Lagrange 4-square theorem. Every integer is the sum, no, every natural number is the sum of squares of 4 integers. The key point here is that notice that the degree has now doubled, right? From originally we had degree 2, and now this guy here has degree 4. So this procedure, it doesn't give a reduction which preserves degree. So of course it does give a reduction of the above problem for degree k. You can reduce it to Hilbert's 10 problem for degree 2k, right? But that's not you know, there is still some room for improvement there. Okay, so now the question is, well, how complicated is this guy? And that there are again several open questions there. If k is at least 4, then we know exactly what's going on. Because if k is at least 4, then we know that this guy is at least as complicated as the Hilbert's 10 problem for degree less than or equals to 4. And as we just discussed a few slides ago, Hilbert's 10 problem for equations of degree less than or equals to 4 is as complicated as the original Hilbert's 10 problem, which we know is equivalent to the halting problem and is maximally complicated and so on. So for degree less than or equals to 4, we know exactly what this is. This is exactly as complicated as the halting problem. But for k equals to 2 or 3, well, it's not so clear. In fact, for k equals to 2, it is known to be solvable. And that is what was proved by Grunewald and Segal. So they showed that there is an algorithm that takes in a Diophantine equation of degree 2 and decides whether it has solutions in the natural numbers. In fact, their algorithm does more. So their algorithm actually tells us whether this equation has finitely many solutions or infinitely many solutions in the natural numbers. So that's something that wasn't what Hilbert's problem was asking for, but actually this algorithm does more than that. And so that also unlocks a whole sequence of questions, right? So, can we do this for other degrees as well? So I want to kind of take this and run with it. Like, this theorem to me motivates the question of asking whether, okay, so instead of looking at Hilbert's original problem about just whether they are solutions, maybe we can look at the more difficult problem of asking whether, well, actually, yeah. So not just do we care about whether there are any solutions at all. We also want to be able to distinguish whether there are finitely many solutions or infinitely many solutions, right? That could be something that we care about. And I want to point out that that actually takes us out of the recursively enumerable setting. Okay, so what do I mean by that? So figuring out whether an equation has a solution is a recursively enumerable thing, in a sense that, well, you have the equation in front of you. You just try each tuple of numbers, and you can just try all of the tuples. And if there's a solution, you're going to find it eventually, and you can halt and figure out that, oh, there is a solution. But figuring out whether there are finitely many solutions or infinitely many solutions doesn't work that way, right? Let's say at some finite stage of your computation, you've managed to find finitely many solutions. Well, I mean, how do you know that you've actually found all of them, right? Maybe there are still more solutions out there. And even if there are more solutions out there, well, how do you know that there are infinitely many or finitely many, right? So basically, this is not something that we can just figure out by brute force, so to speak. This is a more complicated question than the question of whether there is a solution or not. However, this question is still, it can be expressed in the larger framework of a first order sentence. Okay, so here I'm kind of assuming that you have some knowledge of first order logic. And we're going to say a bit more about what first order logic has to do with these things here. Okay, so yeah, what do I mean by this? Okay, say we have a statement which is saying that some Diophantine equation has a solution in Z. We can translate that into a first order sentence phi, which is in this language. So plus and times and 0 and 1 and equals. Okay, so these operations, you can mush them together in appropriate ways to form Diophantine equations. And in order to say that there is a solution in Z, well, we can use existential quantifiers. So we say there exists x1, there exists x2, ... there exists xn, such that p of x1 to xn is 0. So this here is can be written as a first order sentence in this language. And this first order sentence holds in the structure Z with these operations, if and only if this given equation actually has a solution in Z. So, I mean, mathematically, there's very little going on here. This is just kind of a switch of setting. But now, what's different here is that in the first order setting, we can also express more complicated statements. We can have alternations of quantifiers, right? So in front of these existential quantifiers, we can also have some universal quantifiers, and then maybe we can have some existential quantifiers after that. And so this allows us to express things such as P has infinitely many solutions in Z, for example. This is something that you can express with a few alternations of quantifiers. And so more generally, we can define the following. The if you have a structure, so for example, a structure is like Z with all these operations, we can define its first order theory to be the set of first order sentences which are true in the structure. So as a kind of a special case, right, this kind of subsumes the Hilbert's 10 problem, because each of these questions that Hilbert's 10 problem is interested in can be phrased as one of these sentences. And so if we are able to figure out what the first order theory is, well, we would be able to solve Hilbert's 10 problem. Okay, so now let's look at this first order theory for some familiar structures. Okay, so right. So before that, right, we have to talk about some encoding here. So just as we define codes for Diophantine equations, we can also define codes for first order sentences. So if you take a first order sentence, right, think about it as some finite string in some finite alphabet, or even a countable alphabet, and you can encode it as a number. Okay, and that allows us to think about this first order theory as a subset of natural numbers, where so you take the set of all codes of first order sentences which are true in the structure. Then we can ask, well, how complicated is this subset of the natural numbers, right? Is it recursive, or is it recursively enumerable, or is it more complicated than that? All right, so let me tell you about the answers to these questions for some familiar structures. So first, let's start off with Z, right? That's the one that we've been mostly working with. So, well, as I've already hinted, this is not going to be recursive because it subsumes Hilbert's 10 problem. So if this first order theory were to be recursive, right, then that would give us an algorithm to solve Hilbert's 10 problem, because if we are given some Diophantine equation, we want to figure out whether it has a solution. We can translate this question into a first order sentence, and then we can ask the first order theory, well, is this sentence true? And if the first order theory says yes, well, then we know that there is a solution. Otherwise, we know that there's no solution. So that's going to allow us to solve Hilbert's 10 problem, which we know is unsolvable. So therefore this theory is not recursive. And in fact, it is very, very far from being recursive in a way that can be made precise in recursion theory. However, for some other structures, actually, this first order theory is recursive. And this here, I think it's a very interesting fact that we can sometimes compute the first order theory. An example is the complex numbers. So we haven't talked about complex numbers at all in this whole series, but this is a question that we can consider, right, in this setting. We look at the first order theory of the complex numbers together with plus and times and 0 and 1. And so essentially it's a classical result that this first order theory is recursive. Now, why is this? So it turns out that there is an effective procedure. Okay, if I give you a first order formula in this language, plus times 0 and 1, okay, and so this first order formula can have a bunch of quantifiers, right? A bunch of universals, bunch of existentials. There is a procedure to convert such a formula into one with no quantifiers at all. And the fact that this can be done, we call this effective quantifier elimination. This now gives us, if we can do this, right, then it gives us an algorithm to compute the first order theory. Well, why is that? So let's say I give you a first order formula and I'm asking you whether it's true in this structure. Well, the first thing you do is you convert it into a quantifier-free formula. Okay, so this is an effective procedure. And then, well, once you have it as a quantifier-free formula, then you can just straight up compute whether it's going to be true or not. So together, this gives us an algorithm to decide this first order theory. Therefore, as a corollary of this, that tells us that Hilbert's 10 problem for the complex numbers is solvable. So what I mean by this is that suppose if I give you an equation with integer coefficients, and I ask you if there are solutions in the complex numbers, then there's an algorithm to decide whether that's the case. Okay, so far we've looked at the integers and the complex numbers. What else is there? Well, let's look at the real numbers. For the real numbers, there's a little bit of a twist. So this, the structure of the real numbers, together with plus, times, and 0 and 1, this structure does not admit quantifier elimination. So it is not the case that every formula is equivalent to a quantifier-free formula. And here I've given an example of such a formula. So we can write a formula which defines the set of non-negative real numbers, right? We can just say, okay, there is some y such that x is equals to y squared. So this formula is true of exactly those non-negative x. And one can show that this is not equivalent to any quantifier-free formula, essentially because anything that you can do using a quantifier-free formula is going to be like finite or cofinite, basically. So you won't be able to define the non-negative numbers using a quantifier-free formula. There's not a proof, but it is basically the idea behind the proof. So well, what can we do here, right? So the argument on the previous slide that worked for the complex numbers is not going to work here, but a modified argument works. And this here, I think, is a very cool fact, namely that if we now expand the language, to include the ordering, so now the language includes plus, times, 0 and 1, and also the ordering. Okay. In this expanded structure, now we can do quantifier elimination, and in fact, effective quantifier elimination. And this was showed by Tarski. And as a consequence, the first order theory of this structure is recursive. Now that we know that the first order theory is recursive, right, now that we can forget the ordering again, and now we can get the corollary that, okay, the first order theory of our original structure, it is recursive. And therefore, in particular, Hilbert's 10 problem for the real numbers is solvable. So if I give you a Diophantine equation with coefficients, integer coefficients, and ask you if there's a solution in the real numbers, well, there is some algorithm to do it. Okay, so what do we have? So we have for Z, the first order theory is not recursive, but for the complex numbers and real numbers, it's recursive for both. Now, there are several other structures that we might consider. And specifically, so far, we've been working with the language of rings, right? Plus, times, and 0, 1. There are several rings which number theories care about, other than Z. Well, of course, C and R are also among them, but we haven't talked about Q, right? Q is also a ring. And well, there's a reason why I left this to the last, because this is the biggest open problem in this area. So for Q, and also for, if you take subfields of the algebraic closure of Q bar, Hilbert's 10 problem is open. Okay, so we do not know whether there's an algorithm which takes in any equation with integer coefficients and decides whether it has solutions in Q. Similar for any other subfield of Q bar. So that's, yeah, this is the main question in this area, that like if you solve this, then this is definitely going to be in the annals, something like that. Yeah. There has been some quite a lot of related work to this problem, and so I'd like to describe a bit of this to you. One is this is an observation that relates Hilbert's 10 problem for Q to Hilbert's 10 problem for Z, right? So this is kind of a maybe a natural thing to try. If we were able to show that Hilbert's 10 problem for Z reduces to Hilbert's 10 problem for Q, then by the unsolvability of the former, we would know that the latter is also unsolvable. So this proposition, the assumption of this proposition, allows us to carry out such a reduction. So what does this proposition say? Well, let's suppose that the Z, integer Z, is existentially definable over Q. Okay, what do I mean by that? So I mean that in the structure Q, there is some existential formula, some formula that only involves existential quantifiers and no universal quantifiers, which defines Z. Okay, so this formula is going to be true for all of the integers, and it's going to be true of all of the rational numbers. Sorry, it's going to be true of all of the integers, and it's going to be false for all of the rational numbers that are not integers. Okay, so suppose that there was some existential formula that does this. Well, then we could reduce Hilbert's 10 problem for Z to Hilbert's 10 problem for Q in the following way. Okay, so suppose we have some equation P, okay, integer coefficients, and we are interested in whether it has an integer solution. Now we can kind of rewrite this a bit by just saying, well, this has a solution in Z if and only if there are rational numbers x1 to xn, so that, well, first of all, they satisfy the equation, and furthermore, the x1 to xn happen to be integers. Okay, so this is just a trivial rewriting of the first line. But the point now, oh, Tuyao, do you have a question?
Oh yeah, the language is over rings, language of rings, or
yeah, language of rings.
Lesson. Can it be anything? Yeah, okay. Yeah.
Yeah, it's a language of rings. Yeah.
Okay.
Yep. So yeah, so now if we have this, and now using the assumption that Z is existentially definable over Q, which means that we can replace each of these by some existential formula. Okay, and so existential formula, we have a bunch of these. And then we can move the existential quantifiers to the front. And that's going to give us a condition which looks like this. There's some Q, right? So Q is obtained by kind of rearranging these formulas such that Q has a solution in the rational numbers. Okay. And then this is, of course, using very strongly the assumption that this predicate here can be defined using an existential quantifier. Because, well, if we had some other quantifiers in here, like a universal quantifier, then we wouldn't be able to express this as like a Diophantine equation anymore. So that would be a more complicated statement. We wouldn't be able to put it in this nice form. So once we know how to do this, right, then so if we can make this reduction, then since we know that this Hilbert's 10 problem for Z is unsolvable, that tells us that Hilbert's 10 problem for Q must also be unsolvable, because the usual logic, like if Hilbert's 10 problem for Q was solvable, then we could use this to give an algorithm to solve Hilbert's 10 problem for Z. Okay, so this is a very, just a elementary observation, really. And of course, the assumption of this proposition that is an open problem, right? Otherwise, we would be done already. So it is not known if Z is existentially definable over Q. However, it is possible to define Z in Q using a first order formula. So if we allow universal quantifiers, okay, then there are definitions. And I like to say a bit about those definitions. The math involved is too complicated for us, but at least I want to tell you about the history of this work. So the first person to do this was Robinson. So the same Robinson from earlier, Julia Robinson. She defined the integers in the rational numbers using a first order formula of this form. So what I mean is that there was a block of universal quantifiers, followed by a block of existential quantifiers, and then a block of universal quantifiers. Okay, so this is very much not an existential formula, right? In fact, there are two blocks of universal quantifiers here.
What does it look like?
I don't know the details actually. I think it's quite non-trivial. Like it involves non-trivial number theory. It's not like something that you can write down on a slide. Yeah.
All right.
Yeah. Now, this was later improved, actually quite a bit later. So in 2009, Bjorn Prunen, he found a slightly simpler formula. So now this formula only has two blocks of quantifiers now. It's a block of universal followed by a block of existential. And then shortly after that, building on Prunen's work, Königsmann showed that, in fact, there is a formula which uses just a universal quantifier. Okay, so here's the statement of his theorem. This was a paper in the Annals, by the way. So there is a polynomial P, okay, integer coefficients, such that, well, for any x in the rational numbers, x is an integer if and only if, for every rational numbers y1 to yn, P of x y1 to yn is not 0. Okay. So what this gets us is, well, this is a formula with one okay, so I guess here, no, one universal quantifier is not quite accurate. Like I meant one block of universal quantifiers, right? So there are multiple variables here. So technically there are multiple quantifiers, but the point is that there are no existentials. It's all universal. So yeah, again, the proof of these, I think the proof of all of these results involve things in number theory that are very much not elementary. So I don't know how they go. So yeah. So yeah, this is the state of the art, right? That we know how to give a definition using one block of universal quantifiers, but we don't know if there is an existential formula that defines it. And actually, I also don't know what the experts think, like whether they think that it should be, whether there should be such a definition. I'm not really sure.
But do you know who is working on it? Is anyone?
Yeah. Well, so I know I'm about, on the next slide, I'm going to talk about some like another angle that people have taken on this problem. Okay. Yeah. Right. So yeah. And this will actually involve people that you know, I think. So
okay. Yeah. Interesting.
So I mean, these people, I mean, Poonen and Königsmann, they are number theorists, right? But
right.
Yeah. Okay, so yeah, so in this last section of the talk, I'd like to talk a bit about a different angle that people have taken to this problem. So it's not really a direct attack on the problem, but in a way, I think it gives us some kind of heuristic as to what we might choose to believe. And of course, as usual with any heuristic, how you interpret the mathematical result is a matter of personal taste. So, you know, I'm not making any like, you know, I'm not making any claims here as to whether this answer should be yes or no, but I'm just giving this to you. You can interpret it yourself. So, okay, it's open whether Z is existentially definable in Q. Now, we can consider the analogous question not for Q, but for other subfields of the algebraic closure Q bar. Okay, so what about subfields K of Q bar other than Q? Okay, so you know, the algebraic closure, there are many subfields in there. Number theorists, they really care about these, right? Some of these subfields are nicer than others, right? Some of these are like algebraic extensions of Q, things like that. And each of them, they have a ring of integers inside of them. And we can ask, well, is this ring of integers existentially definable in this subfield? And this question was investigated by Eisentrager, Miller, Springer, and Westrick. So this is a collaboration between number theorists and recursion theorists. They showed that in most subfields of the algebraic closure, this ring of integers, so this is the usual notation for the ring of integers in a number field. This ring is neither existentially definable nor universally definable in K. I'll say a little bit about what most means. So right now this theorem is not precise because you need to make this word precise. But let me just say a bit about, okay, what this theorem might be suggesting. Okay, so well, it tells us that for a lot of these Ks, we should not hope to find an existential definition for the ring of integers, right? So if somehow Z was existentially definable in Q, then, you know, there would be, in a sense, a special property of Q. That being said, right, so notice that the second part of the theorem, right, it says that this ring of integers is not universally definable in K for most K. And we already know that the integers Z is universally definable in Q. right? So we already know that there is the potential that that Q has something special that distinguishes it from other number fields. So yeah, so how you interpret this theorem is up to you, but I still think it's a I think it's an interesting mathematical result. Now a bit about what most means. So this is something that this particular theorem, okay, uses a particular notion of most, which is given by a bare category. So this is something that comes from, well, it came from general topology, but nowadays it is also very much used in logic, especially in descriptive set theory. So what you do essentially is you define, you look at the space of all subfields of Q bar, you make it into a topological space, right? You define some topology on it, and then you can talk about what it means to be a meager set with respect to this topology. What does it mean to be a co-meager set in this topology? And so a meager set is, as the name suggests, is like a small set, whereas a co-meager set is like a large set. So what they showed is that for co-meager many subfields, that you have this kind of property. So this here, I think it's an interesting angle on this kind of problem. Okay, so yeah, I think this is all of the math that I wanted to say, and I'd just like to end here with a list of references. So references 1 and 2 have appeared before. If you want to find out about Hilbert's 10 problem, like how it was proved to be unsolvable, I think these are good references. But I've also included some others which I think are quite interesting reads if you're interested in the sort of further directions regarding what people did for Hilbert's 10 problem. Thank you.
Thank you, Jun Le. That was a very nice topic to talk about. Is there any question for Jun Le? Okay. Yeah. So Jun Le, thank you very much.
Thank you. Yeah.
That
Thanks
was
for having me.
Interesting. So this is the last lecture by you. So we'll keep in touch. I'll talk to you again.
Thanks. Right? Yeah, I might come for Patrick's lecture later, but yeah, it depends on whether I can fit my schedule. Yeah. Yeah.
Cool.
All right. Cool. Bye, everyone.
Thanks, Jun Le. Bye.
Bye.
Bye, everyone.